Imagine this. Traveller, you drift into the night and somehow you find yourself here, as if the universe itself placed a gentle hand on your shoulder and guided you to this moment. In just 72 quiet hours, 2 distant stars erupted into naked-eye brilliance. The ground beneath Venezuela trembled twice, and 3I Atlas, the largest interstellar object ever detected, was brushed by a solar storm it should never have survived. What are the odds that all of this would unfold at once? What if it wasn't coincidence at all, but a pattern the cosmos is whispering to those willing to listen? Above us, a silent visitor glides past the edge of Mars, carrying chemistry older than our Sun. Let's drift a little deeper. In the early hours of September 23, 2025, the southern skies revealed an unexpected astronomical event. While conducting his routine observations from New South Wales veteran amateur astronomer John Seach detected a faint point of light that had not been present the night before. The object, later identified as V1937 Centauri, marked the arrival of a nova and eruption that had actually occurred thousands of years earlier, but whose light was only now reaching Earth. Novae are thermonuclear explosions on the surface of white dwarf stars in binary systems, triggered when accumulated hydrogen from a companion star ignites in a sudden runaway fusion event. Although dramatic, these explosions do not destroy the star itself. The white dwarf survives, beginning the long process of accreting material once again. The significance of Seach's discovery became clearer as satellite observatories responded. NASA's Fermi Gamma Ray Space Telescope detected high-energy photons coming from the nova, while the Swift Observatory registered hard X-ray emissions evidence of particle acceleration at nearly relativistic speeds. These signatures confirm the presence of energetic shocks produced as ejected stellar material interacted with the surrounding medium, reaching temperatures of millions of degrees. Such multi-wavelength detections highlight the complex physics behind nova eruptions, where magnetic fields twist, reconnect and channel explosive energy outward into interstellar space. Only days later, another nova emerged, V7994 Sagittari, located in the constellation Sagittarius. Like V1935 Centauri, it brightened to near naked-eye visibility, reaching magnitude 6.2. The discovery of 2 bright novae by the same observer within the same week is statistically uncommon, though not unprecedented. Approximately 10 to 12 novae occur annually in the Milky Way, but only a small fraction reach magnitudes visible without professional equipment. The proximity and timing position and brightness of these 2 events naturally drew the attention of both amateur and professional astronomers worldwide. Following the alerts, observatories began obtaining detailed spectroscopic and photometric data. Spectra revealed broad hydrogen and helium emission lines, typical of nova ejecta expanding at thousands of kilometers per second. Amateur astronomers contributed essential time series photometry tracking how the brightness evolved night by night. Their observations allowed scientists to model decline rates, identify potential dust formation episodes, and classify the novae within the established taxonomies. Collaboration between professionals and amateurs remains crucial in transient astronomy, particularly for phenomena that evolve rapidly. While the sky produced these stellar eruptions, Earth experienced its own form of sudden energy release. On September 24th, a magnitude 6.2 earthquake struck Venezuela at a shallow depth, generating strong surface shaking across 2 nations. A second event, magnitude 6.3, occurred only hours later in nearly the same location. From a geophysical perspective, the pair is explained through tectonic stress transfer. The initial rupture alters stress fields on adjacent segments of a fault system, sometimes triggering a subsequent event shortly afterward. The juxtaposition of twin novae and twin earthquakes during the same week created a sense of cosmic symmetry. However, scientific analysis shows no causal relationship between stellar explosions and seismic activity. The energy arriving from distant novae is minuscule by the time it reaches Earth, comparable to ordinary starlight. Earthquakes conversely originate from the mechanical failure of crustal rock, along plate boundaries driven by geological forces accumulated over years or centuries. The 2 processes belong to fundamentally separate physical domains. Yet the timing raised an important psychological point. Humans are highly attuned to pattern recognition. Our evolutionary history favoured individuals who could detect correlations in nature, changes in weather animal behaviour, or environmental cues that signal danger or opportunity. When unusual events cluster closely in time, even across unrelated disciplines like astronomy and seismology, the human mind naturally searches for meaning. This cognitive trait, while advantageous in many situations, can also produce an impression of connectedness where none exists. Understanding this distinction requires embracing both scientific rigour and cognitive humility. The twin novae were the result of a long-term stellar evolution within distant binary systems. The Venezuelan earthquakes were consequences of stress accumulation along the boundary between the Caribbean and South American tectonic plates. Their simultaneous occurrence reflects coincidence, not connection. However, dismissing the psychological response entirely overlooks the human element of scientific observation, the sense of awe derived from witnessing multiple energetic phenomena unfold at vastly different scales within a short period. The events of that week in 2025 illustrate a broader truth about our relationship with the universe. While physical mechanisms remain independent, the timing of observable phenomena can shape our perception of cosmic complexity. Novae remind us of processes operating across millennia and light years. Earthquakes remind us that even our planet's solid crust is dynamic and unpredictable. When such events overlap, they highlight the diversity of forces shaping our environment, from nuclear reactions on distant stars to tectonic motion within Earth's interior. In the end, the significance lies not in a hidden causal relationship, but in the perspective gained. The cosmos is active on scales that dwarf human experience, yet our instruments and attention allow us to witness these distant events. Observing novae and seismic activity in the same week reinforces our role as interpreters of an ever-changing universe, capable of recognizing both the independence of physical systems and the narratives created by our own minds. The appearance of two bright novae within a single week in September 2025 invited not only observational attention, but deeper analysis of the physics behind these dramatic stellar events. Novae occupy a compelling middle ground, in astrophysics more energetic than typical stellar fluctuations, yet far less catastrophic than supernovae here. They represent a unique cyclic form of stellar instability, one that reveals profound insights into binary star evolution, thermonuclear physics, and the behaviour of matter under extreme gravitational compression. At the centre of every classical nova lies a white dwarf, the dense, compact remnant of a once sun-like star. A white dwarf compresses mass comparable to that of the Sun into a volume roughly equal to that of Earth. This structure is supported not by thermal pressure, but by electron degeneracy pressure, a quantum mechanical phenomenon that prevents electrons from occupying the same quantum states. As a result, the material inside a white dwarf is extraordinarily dense, with a teaspoon weighing tons and temperatures at the surface often exceeding 50,000 degrees Fahrenheit. Yet a nova does not arise from the white dwarf alone. It requires a second star, a companion that continues evolving normally. As this partner ages, its outer atmosphere expands, spilling gas, mostly hydrogen, into the gravitational influence of the white dwarf. Over decades or centuries, this material accumulates into a thin shell on the dwarf's surface. Because of the dwarf's intense gravity, the infalling gas becomes compressed to extreme densities and temperatures. The crucial point is that fusion in this layer is not gradual or steady. Instead, the hydrogen-rich material undergoes runaway thermonuclear ignition. Once a critical temperature is reached around 100 million Kelvin, the reactions accelerate rapidly, releasing a burst of energy equivalent to the Sun's entire output over thousands of years. This sudden energy release ejects the accumulated material into space at thousands of kilometers per second, producing the brightness increase that makes a nova visible from Earth. This process explains many of the features that astronomers observed in V1935 Centauri and V774 Sagittarius. The gamma rays detected by NASA's Fermi telescope and the hard X-rays recorded by SWIFT are signatures of particle acceleration in shock fronts created by the violent ejection of material. As the expanding shell collides with ambient interstellar gas, it generates shocks that function like natural particle accelerators. Electrons spiral through turbulent magnetic fields, producing synchrotron radiation across the electromagnetic spectrum. Such high-energy processes place novae alongside supernova remnants and active galactic nuclei as laboratories for extreme astrophysics. Spectroscopic data from observatories across the southern hemisphere confirm the presence of broad hydrogen and helium emission lines in the nova ejecta. These features indicate high-velocity expansion and the presence of newly formed heavy elements synthesized during the eruption. Over time, the spectra evolve as the ejecta cool and dilute. Forbidden emission lines transitions that occur only in extremely low-density environments begin to appear, offering insights into the late stages of nova evolution. The distances to the September 2025 novae remain uncertain, but available evidence suggests they lie thousands of light-years away. This means the explosions themselves occurred long before recorded human history. The light only reached Earth now because of the immense distances involved. Such temporal dislocations highlight a recurring theme in astrophysics, observing events not as they happen but as they were long ago. A nova we detect tonight may have erupted during the era when early humans first domesticated crops. Amateur astronomers continue to play a critical role in studying these events. Armed with digital cameras, small telescopes and photometric filters, they monitor brightness changes with a temporal resolution that large professional instruments cannot match. These data feed into global networks like the American Association of Variable Star Observers, AAVSUMBO, allowing scientists to build detailed light curves. Such curves are essential for classifying novae, modelling their evolution, and predicting whether they might undergo dust formation episodes, periods when microscopic dust grains condense in the cooling ejecta and temporarily obscure the nova's light. Dust formation in novae is particularly intriguing. Weeks to months after eruption, some novae abruptly dim by several magnitudes. This is not because the explosion ceases, but because dust forms in the expanding shell and absorbs optical light. Eventually the dust disperses or is destroyed by radiation, revealing the underlying remnant once more. Tracking such changes requires consistent monitoring, which highlights the continued importance of global amateur participation. Novae also raise broader questions about the future evolution of white dwarfs. While most novae eject material without threatening the integrity of the white dwarf itself, certain systems called recurrent novae undergo frequent eruptions, often every few decades. In these systems, the white dwarf may gradually approach the Chandrasekhar limit, the maximum mass, about 1.4 solar masses, a white dwarf can sustain before collapsing or exploding as a Type Ia supernova. Such supernovae play a crucial role in producing heavy elements and serve as standard candles for measuring cosmic distances. Understanding nova cycles therefore contributes indirectly to cosmology and galactic evolution. Returning to the events of September 2025, the most striking feature remains the temporal clustering of the two novae. Though statistically uncommon, their near-simultaneous appearance does not violate known astrophysical principles. Binary systems across the galaxy evolve independently, and eruptions occur when internal conditions reach critical thresholds, not when external cosmic events suggest a timetable. Yet the human response to such timing underscores the role of perception in scientific interpretation. The juxtaposition of two stellar eruptions with two powerful earthquakes on Earth in the same week creates an impression of synchronicity. Still, physics maintains clear boundaries. Novae occur at distances so great that their energy when it reaches us is insufficient to influence geological processes. Earthquakes arise from mechanical stress in the crust governed by tectonic motion and regional geology. The convergence of events is coincidental yet psychologically meaningful. What remains is perspective. Novae remind us that the universe contains processes far older and larger than human affairs. Earthquakes remind us that our own planet is dynamic and restless. Observing both in the same week highlights the richness of a universe where multiple systems, each governed by its own laws, evolve in parallel across vast scales. In this sense, the clustering of events is less a cosmic message and more an invitation to observe, carefully, think clearly, and appreciate the complexity of a universe whose phenomena unfold across distances and times beyond ordinary intuition. While the skies delivered two rare stellar explosions in late September 2025, Earth produced its own dramatic events. Within a span of only hours, 2 significant earthquakes struck the same region of Venezuela, capturing global attention and prompting questions about whether the timing bore any deeper meaning. Scientifically, these events are well explained by established tectonic processes, yet their coincidence with the twin novae led many observers to reflect on the broader patterns of an active and interconnected planet. The first earthquake occurred on September 24, 2025 at 22:21 UTC. Measuring magnitude 6.2, it originated at a shallow depth of approximately 7.8 kilometers beneath Venezuela's Zulia state. Shallow earthquakes of this magnitude produce strong surface shaking because seismic waves have little distance to attenuate before reaching populated areas. Reports of swaying buildings, rattling windows, and rapid evacuations appeared across both Venezuela and neighbouring Colombia. Although structural damage was relatively limited, the psychological and logistical impacts were significant for millions of residents. Only 5.5 hours later, at 03:51 UTC on September 25th, a second event struck. This one registered magnitude 6.3, originating from a slightly deeper source, about 14 kilometers beneath the same region. Although deeper earthquakes often produce slightly less surface acceleration, this event remained strong enough to cause widespread concern. The pair represented one of the most notable seismic sequences in the region in recent years. To understand why such twin earthquakes can occur in rapid succession, it is essential to consider the tectonic environment underlying North and South America. Venezuela sits atop a complex interaction zone between the Caribbean Plate and the South American Plate, 2 massive sections of Earth's lithosphere that are continuously moving relative to each other. These motions accumulate stress in the crust over long periods. When stress exceeds the strength of the rocks along a fault zone, rupture occurs, releasing stored energy in the form of seismic waves. The Zulia region lies near several significant fault systems, including the Boconó Fault, the Oca-Pa'an-Con Fault, and the Santa Marta-Bucaramanga Fault system extending into Colombia. These interconnected networks distribute stress across multiple fault segments. When one segment ruptures, it alters the regional stress field, a process known as stress transfer. This can increase the likelihood of a subsequent rupture on an adjacent segment, particularly if it was already near failure. This explanation fits the September 2025 sequence well. The first earthquake redistributed stress in the area, likely increasing stress on a neighbouring portion of the fault system. The second event occurring hours later reflected this new stress equilibrium. Although the magnitudes differed only slightly, the logarithmic nature of the moment magnitude scale means the 6.3 earthquake released nearly twice the energy of the 6.2 event. Following these 2 main events, the region continued to experience aftershocks, including a notable magnitude 5.8 tremor later on September 25th. Aftershock sequences follow well-established statistical patterns described by Omari's law, which states that aftershocks become less frequent over time, but can continue for weeks, months, or even years. The scientific agencies monitoring the events, including the United States Geological Survey USGS, and the European Mediterranean Seismological Center, EMSC, reported small variations in magnitude estimates. Such differences are expected due to distinctions in instrumentation measurement methods and the availability of additional seismic data as more stations report their observations. Magnitudes are often refined in the hours and days after a major event. Although earthquakes are governed by well-understood mechanisms, their emotional and social impacts are significant. Residents across Venezuela and Colombia evacuated homes and high-rise buildings, emergency services mobilized, and governments assessed infrastructure for potential damage. Even when structural destruction is limited, earthquakes create anxiety, unsettle communities, and disrupt daily life. The September 2025 events served as reminders of the necessity for robust building codes, ongoing geological monitoring, and public educations on earthquake preparedness. The coincidence between Venezuela's twin earthquakes and the twin novae observed in the southern sky prompted discussion among the public about potential connections. Scientifically, however, no mechanism exists to link distant stellar explosions with seismic activity on Earth. The energy reaching Earth from the novae is far too small to exert any physical influence on crustal stresses. Likewise, solar storms, though capable of affecting Earth's magnetosphere and upper atmosphere, do not impart forces sufficient to trigger tectonic events. Nevertheless, the clustering of events illustrates an important psychological phenomenon. Humans are predisposed to identify patterns, especially during times of uncertainty or heightened awareness. When unrelated phenomena occur in close temporal proximity, the mind instinctively searches for coherence, even when the underlying processes are entirely independent. While pattern recognition can be a valuable evolutionary tool, it can also lead to overinterpreting correlations that lack physical basis. From a scientific standpoint, the Venezuelan earthquakes fit within broader regional trends. Historical records indicate that the Caribbean-South American plate boundary generates frequent seismic activity. Magnitude 6 earthquakes are not rare in this region, though their timing remains unpredictable. Stress accumulates slowly over decades, and releases suddenly producing sequences that sometimes appear clustered, but ultimately reflect the inherent randomness of fault rupture. Seismologists emphasize the limits of current predictive capabilities. Although earthquake forecasting can estimate long-term probabilities based on fault slip rates, short-term prediction remains impossible. No known precursor, whether geological, atmospheric, electromagnetic, or astronomical, reliably indicates the timing of an impending rupture. Studies have explored many potential indicators, including space weather influences, but none have demonstrated consistent predictive value. What the September 2025 earthquakes reveal instead is the dynamic nature of Earth's crust. Tectonic processes operate continuously, redistributing stress and producing earthquakes of varying magnitudes. This internal activity is analogous in some ways to the dynamic processes observed in stars, both governed by physical laws, both capable of sudden energy release, and both evolving over long time scales. Yet similarities end there. The physical mechanisms are distinct, and one does not influence the other. In the broader context of late September 2025, the twin earthquakes contributed to a week marked by observation analysis and public fascination. The simultaneous appearance of novae and seismic activity highlighted the value of scientific literacy understanding which events are connected, which are independent, and how each fits into the larger tapestry of natural processes shaping our world and our understanding of the cosmos. Ultimately, the Venezuelan earthquakes reaffirm that Earth, like the stars, is a dynamic system shaped by forces far larger than individual human experience. Studying these processes deepens our appreciation of the complex and ever-changing planet we inhabit, one that remains active beneath our feet even as distant stars continue their own cycles of eruption and renewal across the galaxy. While distant stars erupted and Earth's crust released its stored tension, another source of activity shaped the final week of September 2025, our own star. The Sun, often perceived as a stable and unchanging presence in our daily lives, was undergoing one of the most active periods of its 11-year magnetic cycle. Solar Cycle 25 had reached its maximum, a phase characterized by increased sunspots, intense magnetic disturbances, and frequent eruptions of high-energy plasma known as coronal mass ejections, CMEs. Understanding the Sun's behavior during this period is essential for placing the events of late September in their proper scientific context. Unlike the distant novae or the tectonic events in Venezuela, solar activity has direct and measurable effects on the heliosphere, the vast bubble of magnetic influence that encompasses the planet's comets and interstellar material traversing our solar system. During solar maximum, the Sun's magnetic field becomes increasingly complex. Instead of the relatively simple dipole pattern seen at solar minimum, the field becomes tangled, knotted, and multi-directional. Sunspots areas of concentrated magnetic activity appear in large numbers. These regions are cooler and darker than their surroundings, but they serve as anchors for the Sun's most dramatic eruptions. A coronal mass ejection begins when magnetic field lines in the solar corona are twisted by the motion of plasma beneath them. As tension builds, these lines can suddenly realign in a process called magnetic reconnection, releasing enormous amounts of stored energy. The result is the ejection of up to 1 billion tons of plasma into space at speeds ranging from 250 to more than 3,000 kilometers per second. Although these numbers sound abstract, their implications are significant. Fast CMEs can travel from the Sun to Earth in as little as 15 to 20 hours. In late September 2025, space weather prediction models, including NOAA's sophisticated WSA Enlil model, indicated increased solar activity. Multiple CMEs were propagating through the inner solar system, their paths overlapping with regions occupied by Earth-Mars. And for the first time in recorded history, an interstellar visitor, 3 Atlas. These predictions sparked global interest. CMEs have been observed interacting with comets for decades, occasionally producing dramatic effects. In 2007, the European Space Agency's Stereo spacecraft captured a CME slicing off the ion tail of comet Encke. This disconnection event vividly demonstrated how solar wind and magnetic fields can reshape the fragile atmospheres surrounding small icy bodies. When model projections suggested that a late September CME might cross paths with an object not native to our solar system, astronomers took notice. Before examining the potential interaction with 3 Atlas, it is necessary to understand the role CMEs play in shaping the space environment. Earth is protected by its magnetosphere, a magnetic bubble that deflects most of the charged particles carried by the solar wind. However, when a CME strikes the magnetosphere, it can compress, deform, or reconnect magnetic field lines, triggering geomagnetic storms. These storms can disrupt radio communication, interfere with GPS systems, enhance atmospheric drag on satellites, and generate powerful auroras visible across high and sometimes mid-latitudes. The likelihood of such disturbances increases during the equinox months because of the Russell-McFerran effect, a geometric alignment that makes Earth's magnetic field more susceptible to solar wind coupling. Thus, September and October 2025 were already primed for elevated space weather activity, independent of any stellar or terrestrial events occurring in the same time frame. As multiple CMEs were released during this period, space weather forecasters analysed their speeds, directions, and magnetic properties. While some were aimed toward Earth, others were projected to pass through regions occupied by Mars and the inbound trajectory of 3I Atlas. It is important to distinguish between forecasted interactions and observed interactions. At the time, no spacecraft had directly imaged a CME striking the interstellar object. Instead, the prediction was based on model trajectories that placed Atlas within the range of possible CME impact. Scientifically, the potential interaction between solar storms and interstellar material is compelling. A comet or comet-like body from another star system may contain volatiles, isotopic ratios, or structural properties different from those found in comets native to our solar system. If a CME were to strike such an object, it could modify the brightness or shape of its coma and tail. Increased ionization might produce measurable changes in spectral emission lines, offering insight into the chemical composition of material formed around another star. Even without a confirmed interaction, the theoretical implications were significant. Interstellar objects represent rare opportunities to study the chemistry and physics of another planetary system without sending a spacecraft across interstellar distances. A CME acting on such an object effectively becomes a natural experiment, a test of how material forged in distant cosmic environments responds to the magnetic and radiative forces of our Sun. While attention focused on the interstellar visitor, Earth remained under constant monitoring. NASA's Solar Dynamics Observatory SDO recorded high-resolution images of sunspot groups evolving rapidly across the solar disk. The Solar and Heliospheric Observatory SOHO tracked CMEs erupting from the Sun's far side. Meanwhile, the ACE and Dioscoviar spacecraft, located between Earth and the Sun, measured incoming solar wind parameters in real time, providing the first alerts for potentially geo-effective events. Despite the clustering of solar storms, the scientific community maintained clarity. Solar activity was behaving exactly as expected during a cycle near maximum. The timing was notable, but not abnormal for the Sun's magnetic rhythm. The challenge lay not in fitting these events into a narrative of cosmic synchronicity, but in understanding them within the framework of well-established heliophysical processes. Yet the human mind tends to merge events when they occur close in time. Twin novae in the sky, twin earthquakes on Earth, and heightened solar activity created a sense of narrative coherence, a perception of a universe moving in unison. Science, however, separates correlation from causation. Solar activity did not trigger the novae did not influence Earth's tectonics, CMEs did not cause seismic events. Instead, each domain, stellar physics, geophysics, and heliophysics, displayed its own internal mechanisms operating independently. Nevertheless, the convergence provided a rare moment of awareness. It reminded observers that the Sun is not a passive backdrop to life on Earth, but an active dynamic star whose behaviour shapes the entire heliosphere. During solar maximum, its influence expands outward, affecting planet spacecraft and potentially even interstellar visitors passing through. In this way, the events of late September 2025 encouraged a deeper appreciation of the Sun's role as a central driver of space weather. While unrelated to novae or earthquakes, its eruptions highlighted the interconnectedness of solar system environments and the importance of monitoring our star not only as a source of light and warmth, but as a generator of powerful, far-reaching magnetic phenomena. As solar activity intensified in late September 2025, scientists turned their attention toward a visitor. Unlike anything else in the heliosphere, 3II Atlas III confirmed interstellar object ever detected. While the Sun frequently interacts with comets native to our own solar system, this period marked the first time in human history that a coronal mass ejection CME might intersect with an object born around another star. The possibility was more than a curiosity. It represented a rare natural experiment in heliophysics, planetary science, and interstellar chemistry. Interstellar objects are fundamentally different from asteroids and comets that formed inside our solar system. They were shaped by gravitational, chemical, and radiative environments we have never observed directly. Their compositions may carry isotopic signatures from distant stellar nurseries, or from planetary systems with very different histories of radiation exposure, magnetic field cycling, and cosmic ray bombardment. In short, they offer a direct sample of extraterrestrial material, one that arrives without the need for spacecraft to travel tens of thousands of years across interstellar distances. 3I Atlas was first detected on July 1, 2025 by the Asteroid Terrestrial Impact Last Alert System ATLAS. Its orbit immediately marked it as foreign, a hyperbolic retrograde trajectory, with an inclination of roughly 175 degrees moving opposite the direction of planetary motion. This path ensured that the object would spend significant time near the ecliptic plane, the region of space where solar wind density is highest, and where solar storms frequently travel. Unlike Oumuamua, which passed rapidly through the inner solar system in 2017, and Comet Borisov in 2019, which remained relatively distant, 3I Atlas approached a region of intense space weather during one of the most active solar maxima in recent decades. This timing raised the prospect that a CME might interact with the interstellar visitor. Such a collision, while not dangerous to Earth, could dramatically influence the behaviour of Atlas's coma and ion tail. When solar system comets experience CME interaction, the resulting magnetic reconnection can sever ion tails entirely, an effect vividly documented with Comet NK in 2007. Tail disconnection events occur when the magnetic field carried by a CME overwhelms the weaker magnetic environment around a comet, causing the ionized gases to detach and drift away. If 3I Atlas were subjected to a similar encounter, scientists might observe changes in tail structure brightness or spectral emissions. These changes could reveal the relative abundance of volatile species, such as CnCO and CO2, as well as traces of organic molecules or isotopic variations not typically present in solar system comets. In this way, the Sun's magnetic storms become a probing tool, a means of testing how material forged around another star responds to solar radiation and plasma. Forecasting such an interaction, however, depends on modelling. NOAA's WSA Enlil model projected that CMEs released during late September could cross the object's predicted path. Yet models are probabilistic. They do not provide direct confirmation. No spacecraft was positioned to image the encounter in real time. Instead, astronomers relied on ground-based and orbital observatories to detect downstream effects, changes in brightness, coma, morphology, or ion tail geometry. Understanding how a CME might affect an interstellar object requires appreciating the physics of cometary atmospheres. As a comet approaches the Sun, solar heating causes volatile materials within the nucleus to sublimate, forming an expanding cloud of gas and dust called the coma. Dust particles respond primarily to radiation pressure, creating curved tails that follow predictable orbital dynamics. Ionized gas, however, is shaped by electromagnetic forces. Outflowing ions couple to the interplanetary magnetic field IMF, forming a narrow straight ion tail that points away from the Sun. This makes the ion tail an excellent tracer of solar wind conditions. When a CME sweeps past a comet, the IMF undergoes rapid reconfiguration. Magnetic reconnection can disconnect the ion tail, accelerate charged particles, or enhance ionization in the coma. Observing such effects in 3I Atlas may offer not only insights into the object itself, but into heliospheric physics, particularly how the IMF interacts with material outside the solar system. The significance of the potential CME Atlas interaction extended beyond scientific curiosity. It also intersected with active planetary missions. On October 3, 2025, 3I Atlas was scheduled to pass within point 19 AU of Mars, placing the interstellar visitor within range of Mars orbiters equipped with high-resolution imaging and spectroscopic instruments. NASA's Mars Reconnaissance Orbiter MRO and the ESA's ExoMars Trace Gas Orbiter TGO planned opportunistic observations, potentially capturing morphological or compositional changes that might be attributable to solar wind interaction. Although the resolution of these instruments, roughly 30 km per pixel at Atlas's distance, would not allow direct imaging of the nucleus, they could detect large-scale coma structure brightness variations and gas emissions. Combined with ground-based observations from Earth, these multi-point datasets would provide an unprecedented three-dimensional portrait of an interstellar object under the influence of high solar activity. This scientific opportunity was enhanced by the wider heliospheric conditions. Solar Cycle 25 was producing active regions with strong complex magnetic fields and frequent eruptions. The Russell-McFerran effect associated with equinox alignment increased the efficiency of solar wind coupling with planetary magnetospheres and interplanetary objects. In this context, the possibility of observing solar interstellar interactions was not merely an observational coincidence, it was a rare intersection of astrophysical timing and technological capability. Yet it is important to differentiate scientific analysis from coincidence-driven interpretation. The clustering of events, twin novae, twin earthquakes, and heightened solar activity led some observers to speculate about deeper connections. But the physics remains clear. CMEs are products of magnetic stress in the Sun's corona. Novae arise from thermonuclear ignition on white dwarfs in distant binary systems. Earthquakes result from tectonic stress accumulated along crustal boundaries. Each process is internally driven, governed by distinct physical laws, and unaffected by the others. The true significance lies not in assumed causal relationships, but in the convergence of observational opportunity. For the first time in history, an interstellar object traversed the inner solar system during a period of strong solar activity, while multiple spacecraft and ground-based observatories were prepared to collect data. This alignment allowed scientists to examine how the Sun's magnetic output interacts with material from beyond the solar system, an event that will likely become a touchstone for heliophysics and planetary science in the decades to come. In this way, the events of late September 2025 underscore an essential truth of scientific exploration. Breakthroughs often arise not from orchestrated phenomena, but from the fortunate intersection of timing technology and natural cosmic processes. The possible interaction between a CME and 3I Atlas, though not yet definitively observed, demonstrates how the universe occasionally arranges conditions that allow us to learn more about our place within it. By the end of September 2025, the scientific community found itself tracking an unusually dense sequence of natural events. 2 bright novae, 2 significant earthquakes in Venezuela, elevated solar activity, and the passage of an interstellar object through the inner solar system. Each phenomenon was explained by well-established physical principles, yet taken together the sequence created a sense of narrative cohesion, a feeling that the universe was arranging itself in an unusually synchronized way. Understanding this response requires examining the interplay between actual physical processes and the human tendency to perceive patterns. A timeline clarifies the clustering September 23rd Nova Vibe 1935 Centauri brightens to near naked eye visibility. September 24th, a magnitude 6.2 earthquake strikes Venezuela. September 25th, Nova since 94, Sagittarius erupts. Another magnitude 6.3 Venezuelan quake occurs hours later. Late September, solar cycle 25 produces multiple coronal mass ejections directed through the inner heliosphere. Early October, interstellar object Thurfii near Atlas approaches Mars while comet C's 2025 R2 Swan nears its closest approach to Earth. From a physics standpoint, these events are unrelated. The novae originated thousands of light years away in binary systems undergoing thermonuclear runaway. Earthquakes emerge from mechanical stress accumulating along tectonic boundaries. Solar storms resulted from magnetic reconnection in the Sun's corona. And the trajectories of celestial objects followed gravitational dynamics independent of terrestrial processes. Yet the convergence felt meaningful to many observers, precisely because the events occurred close together in time. This sense of meaning arises from pattern recognition, one of the most deeply rooted functions of the human brain. Throughout evolution, identifying patterns carried a survival advantage, recognizing seasonal changes, detecting predator movements, or anticipating environmental shifts. Consequently, human cognition is optimized to find structure even when structure does not exist. This cognitive bias, known as apophenia, leads us to perceive meaningful relationships in random or uncorrelated data. In scientific contexts, apophenia becomes especially evident when multiple dramatic events occur within a narrow window. The mind intuitively links them even when the underlying mechanisms are independent. This does not indicate irrationality. Rather, it reflects cognitive architecture shaped by evolutionary pressures. Recognizing the tendency helps distinguish scientifically valid connections from psychologically compelling coincidences. Scientific method provides a corrective framework. Establishing a causal relationship requires demonstrating a plausible mechanism, consistent correlation, and predictive reliability. None of these conditions apply across the domains of novae tectonic activity, solar storms, and interstellar dynamics. Although the timing was striking and no physical link connects these phenomena, the novae released energy over interstellar distances insufficient to influence Earth's crust. Earthquakes release mechanical forces confined to regional tectonics. Solar activity arose from magnetic instabilities in the Sun's corona. The interstellar object followed an orbital path shaped by galactic gravitational interactions over millions of years. However, the absence of causal links does not diminish the interest or significance of these events. Instead, the clustering provides an opportunity to examine how science communicates uncertainty and probability. Natural processes often occur in clusters due to statistical chance. The universe contains countless independent systems, stars, planets, tectonic plates, magnetic fields, each governed by its own rhythms. Occasionally these rhythms overlap, creating the illusion of synchrony. The scientific mainstream is clear on these matters. The United States Geological Survey (USGS) has repeatedly emphasized that no demonstrated connection exists between solar activity and earthquake occurrence. Decades of empirical studies comparing earthquake catalogues with solar indices have failed to support a causal mechanism. Stellar astronomers maintain similar conclusions regarding novae. Their timing depends on the accretion rates and thermonuclear thresholds within binary systems, not on solar system conditions. Likewise, heliophysicists note that solar storms follow solar magnetic cycles and show no influence from distant stellar or planetary processes. Nevertheless, the psychological pull of synchronicity remains strong not because of ignorance, but because of our innate desire for coherence in a vast complex universe. When events align temporally, they appear to share a narrative structure. This reflects a deeply human impulse making sense of the cosmos by linking disparate phenomena into a unified explanation. Understanding this tendency is critical for scientific communication. When events cluster, public speculation often fills the interpretive vacuum. Without clear explanations, narratives of cosmic significance or hidden connections can proliferate. Addressing these perceptions with transparent evidence-based reasoning allows science to maintain both credibility and public trust. Yet it is equally important to acknowledge that coincidence does not diminish wonder. The September 2025 events illustrate how distinct physical processes can unfold simultaneously across radically different scales. Novae demonstrate the nuclear physics governing stellar evolution. Earthquakes reveal the dynamic nature of the planet's lithosphere. Solar storms highlight the sun's power and its influence on the heliosphere. Interstellar objects showcase the vastness and diversity of material originating beyond the solar system. Observing these processes together allows us to reflect on the richness of the universe. Moreover, the idea of coincidence itself holds scientific value. Random clustering provides insights into stochastic processes, probability distributions, and the ways in which complex systems evolve. Just as earthquakes follow statistical laws like Amori's decay, or Gutenberg-Richter scaling the appearance of novae comets and solar storms, also follows probabilistic patterns. The convergence of these events while striking falls well within the expected variability of natural phenomena distributed across large temporal and spatial scales. This perspective offers a balanced approach to interpreting cosmic and terrestrial events, recognizing the independence of underlying mechanisms while appreciating the narrative impact of their combined appearance. It highlights the need to distinguish between emotional significance and scientific causation, a distinction essential for both scientific integrity and public understanding. Finally, the clustering underscores one of the most remarkable aspects of modern science: our ability to detect, measure, and interpret events across astronomical, planetary, and subsolar scales. In earlier eras, civilizations could only observe bright novae, or feel earthquakes, without understanding their origins. Today, we can track gamma-ray emissions from distant stars, map stress centers in Earth's crust, monitor solar magnetic activity in real time, and calculate the trajectories of interstellar objects entering our solar system. The convergence of such observations in a single week is not a cosmic message, but a reflection of humanity's expanding observational capability. In this sense, the late September 2025 sequence is less a mystery than a milestone, a demonstration of our ability to observe multiple domains of the universe simultaneously. The events invite not speculation about hidden connections, but appreciation for the complexity of natural systems and the growing sophistication of human inquiry. While cosmic events such as novae and interstellar visitors capture the imagination, Earth's own interior remains one of the most powerful engines of natural change. The twin Venezuelan earthquakes of September 24th and 25th, 2025 offered a compelling reminder of the dynamic processes operating beneath our feet. These events, though dramatic, fit within a long and well-studied pattern of tectonic behaviour. Understanding them requires examining both the local geological environment and the broader physics governing earthquake clusters. The first of the two main shocks, a magnitude 6.2 earthquake, originated at a shallow depth of approximately 7.8 kilometres. The shallow focus made the shaking particularly intense across populated regions in Venezuela and parts of Colombia. The rupture likely spanned several kilometres along one of the region's major fault systems, releasing stress that had accumulated over years or even decades. Such stress accumulation results from long-term plate motions, the slow, relentless movement of Earth's lithospheric plates, driven by mantle convection and gravitational forces. Just a few hours later, a magnitude 6.3 earthquake struck almost the same region. Its depth, approximately 14 kilometres, placed it slightly deeper within the crust, but still shallow enough to produce strong surface shaking. The proximity in both time and space is consistent with a well-known geophysical process called static stress transfer. After a major rupture, the stresses redistributed along the fault do not simply vanish. Instead, some nearby segments experience increased shear stress. If such a segment was already close to failure, the first event can precipitate the second. Although the magnitudes differ only slightly, the moment magnitude scale is logarithmic. A 6.3 earthquake releases roughly twice the energy of a 6.2. Together, the two earthquakes collectively released energy equivalent to a single event in the magnitude 6.4, 6.5 range, large enough to capture global attention, yet well within the expected range for this tectonic setting. The regional geology explains why such events occur. Northern South America lies at the intersection of the Caribbean Plate and the South American Plate, where complex relative motions generate frequent seismic activity. The The Zulia region near Lake Maracaibo contains several major faults: the Boconó Fault, which runs northeast-southwest through the Venezuelan Andes, the Oca Ancon Fault, which trends east-west along the Caribbean coast, and the Santa Marta Bucaramanga Fault system, which extends into Colombia. This network accommodates the differential movement of the plates storing and releasing energy in episodic earthquakes. The geological structure beneath Lake Maracaibo further complicates the region. The lake sits within a graben, a down-dropped block bounded by faults formed through long-term extensional forces acting on the crust. These structures accumulate strain unevenly, making them susceptible to clustered seismic events. The presence of rich petroleum deposits in the basin reflects the same geological forces that shape its seismic complexity. Seismological agencies around the world measured the Venezuelan earthquakes using various magnitude scales, leading to small variations in early reports. The moment magnitude scale, MW, used by the United States Geological Survey, USGS, is preferred for large earthquakes because it reflects the total energy released. Other agencies sometimes report body wave or surface wave magnitudes, which can differ slightly. These discrepancies are normal and resolve over time as additional data from seismic stations are incorporated. The aftershock sequence that followed the main events adhered closely to Omori's law, which describes how aftershock frequency decreases over time. The magnitude 5.8 aftershock later on September 25th was typical for a sequence of this size, not large enough to rival the main shocks, but sufficiently strong to maintain public concern and test regional infrastructure. Aftershocks of this magnitude can cause additional damage, particularly to structures weakened by the initial ruptures. Public responses to the earthquakes highlight the human dimension of seismic events. Videos circulated online showing swinging light fixtures swaying high-rise buildings and residents evacuating in the middle of the night. Emergency response agencies coordinated rapid assessments, ensuring that critical infrastructure bridges, power plants, water systems remained operational. Although damage was relatively limited given the magnitudes, the psychological impact underscored the importance of preparedness and resilient infrastructure in seismically active regions. The broader question arising from the Venezuelan events concerns timing. Could something external such as solar storms or cosmic events have influenced the earthquakes? Scientifically, the answer remains firmly negative. Despite periodic claims in the literature, no demonstrable causal mechanism connects solar activity, space weather, or distant astrophysical events to seismic rupture. The stresses required to trigger earthquakes involve forces many orders of magnitude larger than anything that solar storms or cosmic radiation could impart. Earth's crustal stress is governed primarily by plate tectonics, not atmospheric or electromagnetic influences. Although some studies have explored subtle correlations between earth tides caused by the gravitational influence of the moon and sun and seismic activity, such effects are extremely weak and inconsistent. Even at their strongest, tidal stresses are minuscule compared to the forces required to rupture fault systems. The clustering of events in late September 2025, stellar explosions, earthquakes, solar storms, therefore remains a case of temporal coincidence rather than physical interdependence. Statistical clustering is not unusual in complex systems. Earthquakes often occur in sequences, sunspots emerge in groups, and novas erupt unpredictably within the galaxy. Given the vast number of independent processes occurring across Earth and the cosmos, it is inevitable that occasionally several will occur within the same week. This does not diminish the scientific interest of the Venezuelan earthquake sequence. On the contrary, it provides valuable data for understanding the mechanics of stress transfer, rupture, propagation, and regional tectonics. Detailed seismological analyses such as centroid moment tensor solutions help determine which fault planes slipped, how much displacement occurred, and in which directions. Over time, such information contributes to improved seismic hazard assessments. The events also offer perspective. Just as novae remind us of the dynamic processes shaping distant stars, earthquakes reveal the forces operating within our planet. Both phenomena reflect energy accumulation and release, one driven by thermonuclear fusion, the other by geological stress. Neither is connected, yet both are part of the universe's broader expression of physical laws. In conclusion, the Venezuelan earthquakes of September 2025 exemplify the physics of seismic clustering in a tectonically active region. Their timing relative to cosmic events invites reflection, but not causal inference. Understanding them requires recognizing the independence of Earth's interior processes, while appreciating the broader context in which they occurred. A universe filled with dynamic systems, each evolving according to its own rules, occasionally overlapping in ways that capture human attention and curiosity. As September 2025 progressed, scientists monitoring the Sun observed conditions that were fully consistent with the system operating near the peak of its magnetic cycle. Solar Cycle 25, which began in December 2019, had entered its maximum phase, characterized by an abundance of sunspots, active regions, solar flares, and the explosive release of coronal mass ejections (CMEs). Although these phenomena often attract public attention, due to their potential impacts on technology and communications, their timing during this period was neither anomalous nor unexpected. Instead, they represented the natural behaviour of a star at the height of its magnetic activity. A solar cycle lasts approximately 11 years, during which the Sun's magnetic field undergoes a full polarity reversal. At solar minimum, the magnetic field resembles a relatively simple dipole, with field lines emerging from one hemisphere and returning to the other. As the cycle progresses, differential rotation, that is the fact that the equator rotates faster than the poles, twists and shears the field lines. This process generates magnetic complexity, leading to the emergence of sunspots and active regions. By late 2025, the Sun had reached a stage in which its magnetic field was highly tangled and unstable. Sunspots' dark, cooler patches on the solar surface appeared frequently and in large clusters. Each sunspot represents an area of intense magnetic activity, where field lines protrude through the photosphere. These regions often give rise to solar flares, bursts of electromagnetic radiation, and CMEs, which eject billions of tons of plasma into the heliosphere. The 10.7 centimeter radio flux, an important indicator of solar activity, hovered around 180-190 solar flux units during this period. Values above 150 typically signal elevated solar activity, and those approaching or exceeding 200 suggest an environment highly conducive to major eruptions. Such measurements confirmed what solar physicists already recognized from direct imaging. The Sun was operating at a level of magnetic agitation typical of a strong solar maximum. Instruments aboard NASA's Solar Dynamics Observatory (SDO) provided continuous high-resolution images of the solar surface and corona. Observations highlighted active regions with complex magnetic structures, areas where twisted field lines regularly reconnected, releasing energy equivalent to billions of hydrogen bombs. These reconnection events are the driving force behind both flares and CMEs. A coronal mass ejection forms when magnetic field lines in the corona become so stressed that they snap and reconfigure. The release of stored magnetic energy accelerates plasma to speeds of hundreds or even thousands of kilometers per second, propelling it outward into space. During late September, multiple CMEs erupted from various active regions on the Sun's surface. Some were directed toward Earth, while others moved along trajectories that carried them into Mars's orbital region, or toward the path of the interstellar visitor 3I Atlas. To predict CME propagation, scientists use sophisticated numerical models. One of the most widely trusted is the WSA Enlil model, which simulates the evolution of solar wind and plasma through the heliosphere. The model divides space into a three-dimensional grid and calculates how CMEs interact with background solar wind magnetic fields and planetary environments. Although Enlil provides valuable forecasts, it cannot account for every small-scale feature in a CME's structure, nor does it determine with certainty whether a CME will collide with a specific object. Instead, it offers probabilistic predictions that guide observational strategies. The autumn equinox period further contributes to geomagnetic activity due to the Russell-McFerran effect, a geometric configuration that enhances the coupling between the interplanetary magnetic field and Earth's magnetosphere. As a result, even moderate CMEs can trigger strong geomagnetic storms during September and October, increasing the likelihood of auroral displays and disruptions to radio communication. Geomagnetic storms are classified using Noé's G scale, which ranges from G1 minor to G5 extreme. Solar radiation storms and radio blackouts are similarly categorized using the S scale and R scale respectively. During the late September period, several events reached G2 or G3 levels, indicating moderate to strong geomagnetic disturbances. While such storms rarely pose risks to human health, they can affect technological systems, including satellites, aviation communications, and power grids at high latitudes. The connection between CMEs and comets offers an instructive example of how solar storms influence the broader solar system. Ion tails form when solar wind strips electrons from gas molecules in a comet's coma, creating charged particles that flow along magnetic field lines. Solar wind variations thus have an immediate and visible impact on comet morphology. In extreme cases, such as the 2007 CME encounter, with comet Encke complete tail disconnection, events occur demonstrating the dynamic interplay of plasma and magnetic fields. Given this history, the possibility of a CME encountering 3I Atlas sparked considerable interest. Although no direct visual confirmation existed at the time, model projections suggested that at least one CME might cross the object's trajectory. If such an interaction occurred, observable consequences might include increased coma brightness, changes in ion tail orientation, or enhanced spectral emission lines due to elevated ionization levels. These changes would reflect not only the nature of the CME, but also the chemical composition and structure of the interstellar object information that scientists rarely have an opportunity to study. Solar maximum conditions also influenced observational efforts at Mars, where orbiters such as NASA's Mars Reconnaissance Orbiter MRO and ESA's ExoMars Trace Gas Orbiter TGO prepared to observe the interstellar visitor during its flyby. Understanding how Atlas responded to solar wind and potential CME exposure would help characterize its surface composition, volatile content, and outgassing behavior. Even if the morphological changes were subtle comparing observations across multiple vantage points, Earth-Mars orbiters and ground-based telescopes offered an unprecedented multi-geometry dataset. Importantly, none of this activity deviated from well-established physical principles. Solar maximum is known to produce frequent CMEs. The Sun's behavior was consistent with its magnetic cycle, and the timing of eruptions reflected internal solar processes, not external triggers. The clustering of solar activity with seismic and astronomical events was striking, but scientifically unconnected. While the Sun influences Earth's magnetosphere and technological environment, it exerts no known force capable of triggering earthquakes or affecting distant novae. Instead, the significance lay in opportunity. Solar maximum provided a naturally active environment for observing how CMEs propagate and how they interact with heliospheric objects, including for the first time an interstellar visitor. The overlapping events created a moment in which the Sun's behaviour could be studied in conjunction with broader cosmic dynamics. Ultimately, the Sun's activity in late September 2025 underscored a fundamental reality of our solar system. We inhabit the extended atmosphere of a dynamic star. Solar cycles shape everything from auroras to satellite operations, from radio communication to the behaviour of comets and interstellar objects. Observing this activity alongside other natural events offered a unique window into the layered complexity of the heliosphere, a system governed by magnetic fields, plasma flows, rotational dynamics, and the constant interplay of energy and structure. Predicting the behaviour of an interstellar object is fundamentally different from modelling the evolution of comets or asteroids that formed within the solar system. When 3I Atlas was discovered in July 2025, astronomers were confronted with a body whose chemical history, structural integrity, and thermal properties were shaped in an environment far beyond the Sun's influence. As Atlas continued its trajectory toward the inner solar system, scientists faced a challenge that demanded both innovation and caution. How do you model something with no direct precedent? Traditional comet modelling relies on assumptions derived from decades of observations. Solar system comets tend to exhibit predictable patterns of outgassing as they approach the Sun, producing comeas, and tails shaped by the interplay of sublimation solar radiation and the solar wind. Their volatile content, primarily water carbon monoxide and carbon dioxide, has been measured extensively. Similarly, their dust-to-gas ratios, nucleus sizes and rotational behaviours fall within relatively constrained ranges. In contrast, interstellar objects, ISOs, defy these expectations. Both previously observed ESOs Oumuamua 2017 and Borisov 2019 behaved unusually. Oumuamua displayed non-gravitational acceleration without detectable outgassing, while Borisov exhibited an exceptionally high carbon monoxide abundance compared to typical solar system comets. These anomalies underscored a critical point. Models built on solar system norms may not apply to material formed around other stars. For Thury's atlas, the first step in prediction was orbital characterization. Using early astrometric data, scientists confirmed a hyperbolic trajectory with an eccentricity significantly greater than one clear evidence of interstellar origin. Its retrograde inclination meant it approached from a direction nearly opposite the solar system's rotational plane. This geometry increased the potential for interaction with solar wind disturbances, as Atlas would pass through regions of dynamic magnetic field activity, while the Sun remained near cycle maximum. Once the orbit was defined, attention turned to the physical parameters of the object. Early observations suggested that Thury Atlas possessed a diffuse coma at a relatively large distance from the Sun, possibly indicating the presence of highly volatile ices such as nitrogen, methane or carbon monoxide. Such constituents sublimate at lower temperatures than water ice, meaning Atlas could become active at distances where typical solar system comets remain inert. If confirmed, this composition would align more closely with Pluto, like bodies formed in cold outer regions of other star systems. However, a persistent challenge involved nucleus detection. At Atlas's great distance and small angular size, even large telescopes struggled to resolve the nucleus. As a result, scientists relied heavily on indirect measurements: coma, brightness, expansion, velocity, and gas emission spectra. These data allowed researchers to estimate nucleus size, outgassing rates, and dust production. Yet the uncertainties remained significant. With no prior information about Atlas's structure or cohesion modelling, its potential fragmentation or mass loss carried substantial uncertainty. To address these unknowns, researchers employed probabilistic modelling, generating a range of scenarios based on different assumptions about composition, internal strength, thermal conductivity, and rotational dynamics. These models helped predict how Atlas might respond to solar heating, solar wind, and potential CME encounters. They also provided estimates for changes in brightness tail morphology and coma density as the object approached perihelion. A central question concerned non-gravitational forces, small accelerations caused by asymmetric outgassing. Comets emit gas jets that impart thrust, subtly altering their trajectories. Accurate trajectory modelling depends on quantifying these forces. For Thury Atlas, non-gravitational acceleration would reveal information about volatile content and activity levels. As September progressed, astronomers analysed Atlas's orbital residuals, tiny deviations from purely gravitational models, to assess whether such forces were detectable. Early hints suggested mild perturbations, but distinguishing these from measurement noise required continuous observation. Another modelling challenge involved rotation. The spin state of an interstellar object influences how sunlight heats its surface, how volatiles are released, and how jets develop. Irregular rotation can complicate tail formation and induce complex time-variable coma features. Without direct imaging of the nucleus, scientists again relied on photometric variations, brightness changes across days or hours which can reveal periodicity. If Atlas possessed a long rotation period or a chaotic tumbling motion, its behaviour could differ substantially from conventional comets. Beyond physical modelling, researchers also considered thermal evolution. Atlas travelled through interstellar space for millions of years, at temperatures only a few degrees above absolute zero. As it approached the Sun, its surface warmed rapidly, creating steep thermal gradients. Such gradients could induce structural stress cracking or sudden fragmentation events. Solar system comets often fragment when internal pressure overwhelms surface strength. Atlas, shaped by an entirely different history of irradiation and cosmic ray processing, might behave differently. The final set of predictions involved interaction with the solar wind. As Atlas moved deeper into the inner heliosphere, the density and velocity of the solar wind increased. During solar maximum, the magnetic field carried by the solar wind becomes especially turbulent. If Atlas encountered a CME, the interaction could reshape its ion tail, increase ionization rates, or produce visible disturbances. By modelling CME trajectories using tools like WSA, Enlil researchers constructed possible timelines for such encounters, each with unique observational signatures that telescopes could detect. Despite these uncertainties, the scientific community approached Atlas not with expectation of anomaly, but with an appreciation for the unprecedented. Predictive models were not guarantees. They were frameworks designed to interpret data as it emerged. The strength of modern planetary science lies not in eliminating unknowns, but in preparing to recognise patterns when the unknown reveals itself. Ultimately, modelling 3I Atlas highlighted the intersection of astronomy, heliophysics, thermodynamics, and probability theory. It demonstrated how scientific understanding expands through careful observation, comparative analysis, and the willingness to revise theories in light of new evidence. In this sense, Atlas served not merely as an interstellar visitor, but as a reminder of the scientific process itself, iterative, humble, and always anchored in the pursuit of clarity amid the vast complexity of the cosmos. As 3I Atlas drifted deeper into the inner solar system, its path curved toward a rare encounter that observers had anticipated for months. On October 3, 2025, the interstellar visitor would pass near Mars close enough for the Red Planet's fleet of orbiting spacecraft to turn their instruments toward it. This moment was unprecedented. Never before had an object from another star system passed within range of multiple active orbiters capable of coordinated scientific observation. Oumuamua had raced through too quickly and Borisov had stayed too distant. Atlas, by contrast, entered a region where telescopes around two different worlds could examine it together, providing a multidimensional view impossible in previous encounters. Mars offered a unique advantage as a planetary observatory. The orbiters circling it, NASA's Mars Reconnaissance Orbiter, ESA's ExoMars Trace Gas Orbiter, and potentially MAVEN carry instruments designed to study surface minerals, atmospheric gases, ionized particles, and solar wind interactions. None were created with interstellar objects in mind, yet their sensors could detect subtle signatures of gas release dust scattering and ion tail behavior. Even though the visitor remained tens of millions of kilometers away, these spacecraft could measure spectral fingerprints of molecules such as carbon, monoxide, carbon dioxide, and cyanogen clues that might reveal whether Atlas carries the chemistry of another stellar cradle. Earth and Mars, separated by tens of millions of kilometers, offered different angles of observation. Their distinct phase geometries allowed astronomers to view Atlas's coma and tail from multiple directions, helping reconstruct their three-dimensional structure. Differences in brightness scattering and ion alignment between the two vantage points became part of a larger puzzle: how an interstellar body behaves under the influence of our sun's light and our solar wind's touch. Mars's position made it possible to see features that Earth-based telescopes could not, especially the fine orientation of faint ion structures shaped by magnetic field lines. At the same time, Mars's unusual magnetospheric environment opened the possibility of indirect detection. Unlike Earth, Mars does not possess a global magnetic field. Instead, it responds to the solar wind within a induced magnetosphere, a delicate shifting bubble shaped entirely by solar activity. During solar maximum, this bubble becomes turbulent, filled with magnetic waves and charged particle flows. If Atlas's emitted ions intersected regions of varying solar wind density orbiters such as MAVEN, might detect subtle changes in particle populations or magnetic fluctuations. Although speculative, these measurements could offer insight into how foreign material behaves inside an active heliospheric environment. Back on Earth, telescopes continued their steady watch. Observatories across multiple continents tracked Atlas's brightening as it moved inward. Spectrometers searched for the standard emissions of comets' cyanogen diatomic carbon-oxygen-bearing molecules, but also watched for deviations that might hint at unusual isotopic ratios or unexpected compounds. The Hubble Space Telescope monitored ultraviolet emissions while the James Webb Space Telescope looked for deep infrared signatures associated with ices and organic molecules. Even modest differences from typical comet spectra could reveal the chemical fingerprints of another star system carried intact across interstellar space. As brightness measurements accumulated, scientists refined their thermophysical and orbital models. Early tracking had hinted at non-gravitational forces signs that Atlas was gently accelerating under the influence of uneven gas jets. Precise analysis helped estimate the magnitude and direction of these emissions, revealing details about how the nucleus spins how it warms, and how ancient ices respond to sunlight after millions of years in darkness. These models also informed simulations that predicted how the coma might evolve, how the ion tail might respond to solar wind turbulence, and how sudden eruptions of gas might alter the trajectory of an interstellar traveller. One complication was Atlas's retrograde orbit. Because it moved opposite the direction of the solar wind, its relative velocity was unusually high. This configuration increased the likelihood of strange ion tail behaviour, including distortions, sudden realignments, or even disconnection events if struck by a coronal mass ejection. The Mars encounter therefore became a perfect test environment, a multi-world laboratory, operating during one of the Sun's most active periods with spacecraft in different positions, ready to detect the effects. In many ways, the true significance of the Mars flyby was not a single measurement or a single observation, but the coordination itself. Humanity had never before observed an interstellar visitor from both Earth and another planet simultaneously. Data flowed from orbiters, ground telescopes, space-based observatories, and solar monitoring instruments positioned millions of kilometers apart. Together they created a layered mosaic of information that could not have been obtained from any single viewpoint. The flyby became a demonstration of what modern astronomy can achieve. It allowed scientists to test competing theories about interstellar comet chemistry, to study real-time solar wind interactions under peak activity, to refine models of non-gravitational orbital behaviour, and to examine how material formed around other stars responds to the radiation of our own Sun. Atlas did not need to be visually spectacular to be scientifically profound. Its value lay in the insights it offered, and the cooperation inspired a coordinated multi-world investigation that hinted at the scientific possibilities of future decades. In the end, Atlas's passage by Mars symbolised humanity's growing ability to study the universe not only from Earth, but from the expanding network of robotic explorers we have placed throughout the solar system. An object born around a distant star arriving by chance in our neighbourhood became the subject of a planetary symphony of observation, and in that moment the solar system itself seemed to act as a single, unified observatory, quiet, precise, and waiting patiently for the next traveller from the long, cold darkness between the stars. During late September and early October of 2025, a strange pattern emerged in the sky and beneath the Earth, one that drew the attention of astronomers, seismologists, and quiet observers across the world. It began with two sudden stellar eruptions, V1635 Centauri and V1794 Sagittarii, bright enough to be noticed by amateur eyes in dark southern skies. Their light had travelled for thousands of years across interstellar space before reaching our telescopes, yet both arrived within days of each other, as if by cosmic agreement. Almost immediately after these eruptions, the ground in Venezuela trembled twice in rapid succession, releasing energy equivalent to multiple nuclear weapons. At the same time, coronal mass ejections threaded through the inner solar system, brushing the regions where 3i Atlas, the newly discovered interstellar visitor, was quietly passing. Then came October's promise, a bright comet approaching Earth, a solar maximum unfolding overhead, and the interstellar traveller moving toward its flyby of Mars. To the human mind, such clustering feels meaningful. Our brains evolved to search for patterns long before we learned how to measure them. In ancient times, people believed comets foretold famine, eclipses announced the anger of the gods, and earthquakes responded to disturbances in the heavens. That instinct persists today, even when layered beneath scientific understanding. When dramatic events unfold close together, two stars erupting, two earthquakes striking a visitor from another star sweeping past Mars, the mind instinctively begins to form connections. It is not irrational, it is deeply human, yet the scientific explanations underlying these events remain independent. The twin nova eruptions occurred because white dwarf stars had accumulated enough hydrogen from their companions to ignite explosive nuclear fusion on their surfaces. The Venezuelan quakes ruptured because stress had accumulated along the complex fault systems of the Caribbean-South American plate boundary. Solar storms erupted because tangled magnetic fields in the sun's corona snapped and released billion-ton clouds of plasma. And Threes Atlas approached our inner solar system simply because orbital mechanics dictated its trajectory long before recorded human civilization existed. Each phenomenon had its cause, none required the others. Still, the timing raised questions worth contemplating. Why do certain weeks feel unusually full of cosmic motion? Why does a sequence of unrelated events create the impression of a narrative, a story the universe seems to be telling? Cognitive science offers one answer. Humans are pattern-making animals. We connect scattered points into constellations, both in the sky and in meaning. When something unusual happens twice, it becomes a coincidence. 3 times and the mind begins to whisper, perhaps these pieces belong together. Perhaps something larger is unfolding. But coincidence does not imply causation. The United States Geological Survey maintains that no physical mechanism links space weather to earthquake occurrence. Seismological studies across decades show no consistent correlation between geomagnetic storms and seismic clusters. Solar physicists emphasize that coronal mass ejections follow solar cycles, not seismic ones. Astronomers affirm that nova eruptions obey stellar physics, unrelated to events on Earth. And yet acknowledging the independence of these processes does not diminish the emotional significance of their convergence. The cosmos does not speak in human metaphors, but humans interpret the cosmos through narrative frameworks. And sometimes the timing of events creates a narrative bridge that is difficult to ignore. Understanding these patterns requires a delicate balance between wonder and skepticism. Scientific reasoning depends on separating observations from assumptions. We can marvel at the beauty of the overlapping events without assigning them causal relationships. The 2 novas erupted because white dwarfs engage in thermonuclear cycles. The twin Venezuelan earthquakes occurred because variations in crustal stress reached their threshold. The coronal mass ejections emerged because of magnetic reconnection in solar plasma. And 3 Atlas continued its inbound trajectory toward Mars because gravity had no reason to behave differently. Yet there is also value in recognizing how these events shape human perception. The coincidence of multiple dramatic phenomena invites reflection on our place in a dynamic universe. We live at the intersection of stellar processes, tectonic forces, and solar activity. We belong to a world shaped by energies far larger than ourselves. The clustering reminds us of the scale of natural processes that surround us. Processes that unfold whether or not we are watching, whether or not we understand. This convergence also highlights a new era of human capability. For the first time in history, we can monitor nova eruptions across the electromagnetic spectrum, track earthquakes worldwide, in real time follow solar storms as they leave the sun, and observe interstellar objects as they pass through our neighbourhood. Earlier civilizations witnessed the same kinds of events, but lack the tools to connect them or to understand their physics. Today we inhabit a world where global networks of telescopes, satellites and sensors allow us to watch the universe breathe in synchrony and silence. There is a quiet truth within this convergence. Nothing extraordinary may have happened, yet the experience felt extraordinary. The timing created a sense of coherence, an illusion of cosmic choreography. But illusions can illuminate the human condition. They remind us that we stand on a fragile planet orbiting a variable star in a galaxy filled with countless stellar lives and deaths. They remind us that earthquakes and nova eruptions, though unrelated, both arise from the fundamental physics of matter under pressure. They remind us that solar storms and interstellar visitors intersect not because they are destined to, but because space is vast and filled with motion. In the end, perhaps the significance of these events lies not in physical connection, but in perspective. The clustering shows how easily the universe can appear to align when our focus momentarily narrows. It invites humility, curiosity, and a renewed sense of scale. and it encourages us to observe quietly without rushing toward conclusions. The universe often feels like it is speaking to us, but sometimes its voice is simply the echo of our own pattern-seeking minds. For as long as humans have studied the sky, a quiet question has lingered at the edges of both science and imagination: could the storms on our sun influence the quakes beneath our feet? It is a question that resurfaces every time solar flares erupt, or when earthquakes cluster unusually close together. And during the final week of September 2025, when twin solar storms and twin Venezuelan earthquakes appeared within hours of each other, the question returned once more. But to understand it clearly, we must separate intuition from physics and wonder from evidence. The idea itself is understandable. Solar storms, those fast-moving waves of charged particles, can reshape Earth's magnetic field, disturb radio communications, brighten the aurora, and influence satellites orbiting far above us. Earthquakes, meanwhile, can shake cities, rupture ancient rock and release energy equivalent to nuclear detonations. When two powerful forces occur in the same week, the mind naturally seeks connection. Yet science demands a patient and disciplined approach, one that distinguishes what feels meaningful from what is actually measurable. Researchers have explored the solar seismic connection for decades. They have compared earthquake catalogues against solar flare lists, solar wind records, and geomagnetic storm indices. Patterns occasionally appear: a spike in seismic activity following a geomagnetic event here, a regional cluster lining up with a solar flare there. But nearly every statistically significant pattern weakens when examined with more data or tested in a different region. What looked like correlation often dissolves into coincidence. The key issue is mechanism. For a solar storm to trigger an earthquake, it must somehow influence the stress locked deep within Earth's crust. But earthquakes occur because tectonic plates grind, collide, and stretch over decades, building pressure slowly until rock finally fractures. The stresses involved are enormous, far beyond anything solar wind pressure could meaningfully alter. Even the strongest geomagnetic storms only produce magnetic field variations measured in nanoteslas and changes in crustal stress. Measured in microstrains, numbers so small, they're completely overshadowed by the daily motions of tides, atmospheric pressure, fluctuations, and even the load of seasonal snowfall. Some scientists, however, continue to explore subtle possibilities. One hypothesis suggests that sudden drops in solar wind density, when a dense, fast-moving stream suddenly gives way to slower, thinner plasma, could briefly change electromagnetic pressure on Earth's magnetosphere. This, in theory, might produce tiny, electromagnetic disturbances that penetrate the crust and influence rocks under tension. But every step in this chain loses magnitude. By the time these influences reach a fault system kilometers underground, the effect is so small it is indistinguishable from noise. Another idea examines induced electrical currents. During geomagnetic storms, electric fields can form in the ground, especially in regions with conductive rock or underground water systems. These currents could in theory affect pore pressure or rock strength. Yet again, the magnitudes remain tiny, far too small to unlock a tectonic fault, unless it was already just moments away from failure. There is one area, however, where space and Earth undeniably connect tides. The gravitational pull of the Moon and Sun can alter stress along fault lines. These tidal stresses are measurable, and in some regions they slightly increase the probability of earthquakes during certain lunar phases. But tidal effects originate from gravity, not electromagnetic disturbances. And even then, they do not cause earthquakes, they only modulate timing for faults already on the verge of rupture. This illustrates the core issue: earthquakes are governed primarily by geology, not by external forces. Faults rupture when long accumulated stress surpasses rock strength. External influences, whether atmospheric, tidal, or solar, are minuscule compared to the immense forces generated by tectonic motion. That does not mean the question is closed forever. The universe often reveals connections we once thought impossible. But for now, the most honest scientific position is one of humility. No convincing evidence shows that solar activity can meaningfully trigger earthquakes. If any connection exists, it is subtle, conditional, and likely insignificant compared to the dominant tectonic processes shaping Earth's crust. Still, the timing of events in late 2025 invited reflection. Solar storms illuminated auroral skies, while Venezuelan bedrock shook twice in a single night. Their convergence felt poetic, as if two worlds, the deep earth and the open sky, responded to the same hidden rhythm. And though science tells us this rhythm is coincidence, the emotional resonance remains. Humans are storytellers by nature. When the cosmos stirs above and the earth trembles below, it is natural to wonder whether both are part of a single unfolding story. Perhaps the lesson lies not in seeking connections where physics finds none, but in appreciating the intricate systems that compose our world. A restless star whose magnetic storms ripple across space, and a living planet whose ancient plates continue their slow, unstoppable drift. Their dance is not coordinated, yet both remind us that we inhabit a universe built on motion, subtle, powerful, and often beyond our comprehension. When cosmic and terrestrial forces rise at the same time, we may feel as though the universe is speaking. But sometimes it is simply reminding us that we are listening. When two novas erupted in the southern sky during late September 2025, some wondered whether such distant explosions could influence Earth in any measurable way. It is a natural question. Stellar eruptions release unimaginable energy, thermonuclear flashes bright enough to outshine entire star systems. And when events in the heavens overlap with events on Earth, the human mind instinctively searches for meaning. Yet to understand these nova eruptions, we must examine the scales involved distance, energy, and time, and remind ourselves that cosmic spectacle does not always imply cosmic consequence. A classical nova occurs when a white dwarf star dents and collapsed siphons hydrogen from a nearby companion over centuries or millennia. Eventually, the accumulated gas ignites in a runaway thermonuclear flash. For a moment, the system brightens by factors of tens of thousands. By human standards, the energy released is staggering equivalent to the sun's total output over 10,000 years compressed into a single burst. But the vastness of space dilutes even the most violent events. V1935 Centauri and VISA 994 Sagittarius sit thousands of light years from Earth. Their explosions occurred long before the first human civilizations took shape, long before writing, or cities or calendars. What we witnessed in 2025 was ancient light finally reaching our world after travelling across the quiet void for millennia. By the time that light arrives at Earth, its energy has spread across a sphere so immense that what reaches us is barely more than a whisper. The entire flux from both novas combined is less than the energy of sunlight striking your skin during a single second. Even a flashlight held at arm's length would deliver more energy. These eruptions dazzled telescopes and stirred the imaginations of observers, but they had no capacity to alter Earth's atmosphere, climate, or geological systems. They simply arrived luminous, distant, and scientifically fascinating. Some speculate about larger stellar events, supernovae powerful enough to disrupt atmospheric chemistry or damage the ozone layer. Such events are theoretically capable of influencing Earth, but only if they occur within about 50 light years. Anything much farther fades into harmless background light. The novas of 2025 were thousands of light years away, far outside any danger zone. Their photons illuminated our night sky, but their physical effects ended long before they reached us. Still, stellar explosions can leave traces in Earth's geological record, but only over immense timescales. Cosmic rays accelerated by ancient supernovae sometimes embed their signatures in ocean sediments or ice layers. Radioisotopes like iron-60 have been found in deep sea crusts, suggesting that millions of years ago, a nearby supernova may have showered Earth with energetic particles. These influences unfold over epochs, not over days or weeks. They speak to the slow rhythms of galactic evolution, not to immediate impacts on human timescales. This distinction matters. The novas of 2025 captivated observers not because they altered our environment, but because they appeared during a week already filled with cosmic and terrestrial activity. The timing felt meaningful. 2 stellar eruptions, 2 Venezuelan earthquakes, solar storms crossing the inner heliosphere, and an interstellar visitor drifting toward Mars. It was easy to imagine that these events might somehow be linked, as if the universe had suddenly become more alive, more dramatic. Yet such connections dissolve under scientific scrutiny. The eruptions were ancient, the quakes were geological, the solar storms followed magnetic cycles, and 3I Atlas travelled on a trajectory determined long before these nova photons even departed their stars. And yet, the convergence invites a deeper, more human reflection. It reminds us that the universe is not static, but constantly unfolding. Stars explode, faults rupture, comets brighten, and solar storms sweep through space, all governed by laws older than Earth itself. The clustering of these events does not imply causation, but it does highlight the delicate role our species plays as observer. We are beings capable of noticing patterns even when nature offers none, capable of creating narrative even when physics provides pure independence. Perhaps the true significance of those September novas lies not in what they changed, but in what they revealed, that we live within a restless galaxy filled with ancient light and ancient forces, that our sky is a window into events long past, and that sometimes the universe chooses the same week to remind us of its scale, its history, and its silence. They arrived when they arrived, not because we were meant to see them, but because the cosmos proceeds on its own vast schedule. What we make of that coincidence is the part that belongs to us. Traveller. We've drifted a long way tonight. From erupting stars to trembling ground to the silent path of Three-Eye Atlas, we've watched the universe move in ways that feel almost intentional. And yet the deeper truth is simpler. The cosmos is always unfolding, always whispering, always carrying stories older than memory. You and I are just fortunate enough to witness a small part of it. As you rest, remember that nothing out there is finished, new light is already on its way, new mysteries already forming in the dark. Thank you for listening, observer. Rest well, stay curious, and let the universe keep watch.